In this lesson we're going to look at what we mean by a homologous series, and in doing so we're going to make a rapid review of the 4 different organic groups that we've been looking at in this unit. That is to say, the alkanes, the alkenes, the alcohols and the carboxylic acids. Okay, so first of all, what is a homologous series? Well, it's a group of molecules with similar chemical properties, and they have similar chemical properties because they have the same functional group. So quickly, let's look at these functional groups and the resulting chemical properties. So the alkanes consist of carbon and hydrogen bonds and carbon-carbon bonds. This actually makes them quite unreactive and a little bit uninteresting from a chemical point of view. They are useful for fuels. So alkanes will burn in oxygen to form carbon dioxide plus water always. I can't balance that equation because I haven't specified the type of alkane here, but you will always get carbon dioxide and water produced. Okay, looking at the chemical properties of the alkenes, well, their functional group is the carbon-carbon double bond. That's what characterizes the alkenes. They will always have either one or more double bonds in their chains, and these are reactive because of that double bond. Okay, that makes them much more useful chemically, and we can perform, because of this double bond, as you will see in other lessons, addition reactions with hydrogen to produce alkanes, with steam, that's water under high pressure and temperature, to produce alcohols, and with halides to produce haloalkanes. Now, the alkenes also form monomers which can be used to produce addition polymers, which we will look at in the lesson on polymerization. So alkenes are very useful for forming polymers and plastics. Next we have the alcohols. They're characterized by the hydroxyl group, that's the OH group. These can be dehydrated to form alkenes, and they can be oxidized to form carboxylic acids. Now, as I said earlier, we'll look at these specific reactions when we come to look at the alcohols and the carboxylic acids on their own. Also, alcohols can be used as fuels. So, as with the alkanes, an alcohol, when it burns in oxygen, produces carbon dioxide and water. Always the same products. Next we have the carboxylic acids. These are characterized by the carboxyl group, which is C double bond oxygen, then O and H, hydroxyl group, where the carbon is joined to the oxygen by a single covalent bond and the oxygen to the hydrogen by a single covalent bond. Okay, as the name suggests, these are all acids. They are weak acids, and they will react with alcohols to produce esters. So there we have it. Each homologous series has a functional group which dictates its particular chemical properties, which gives that homologous series similar chemical properties. Now, not only do they have similar chemical properties, but they will also have similar physical properties. So first of all 4 families have similar melting points and boiling points. Okay, and what will happen is there will be small changes in these melting points and boiling points as you move down the group. So we can see this if we have a look at a table of their boiling points. So we've got the number of carbons in the chain here, and we've got the various groups here, and you can see in each homologous series, as the number of carbons increases, the boiling point increases by more or less the same amount. Whether you're looking at the alkanes, alkenes, alcohols or carboxylic acids, you get the same incremental increases in boiling point as you move down that series. You'll also notice there is a difference in boiling points between the alcohols and the alkanes and alkenes. That's due to the presence of the hydroxyl group. I'm not going to go into the details of that now because we're not doing A-level chemistry, but that tends to increase the forces that hold the molecules together. And the carboxyl group increases these forces still further by allowing the molecules to form what is known as dimers, which you can look at in the session on carboxylic acids. Okay, although that really is A-level territory. Okay, but these groups tend to make the boiling points of these molecules higher than the alkenes and alkanes. Okay, and another physical property which we can address is the solubility of the alcohols and the carboxylic acids. These are soluble in water. At least we're talking about the first four members in the group. And this solubility is due to the presence of the hydroxyl and the carboxyl functional groups. That helps them to dissolve in water. And we can also note that their solubility decreases with chain length. So the third important point with regard to homologous series is that all homologous series can be represented by a general formula. So we're just going to have a look at the general formulas for the four groups that we've been looking at in this unit. First of all, the alkanes, which start off with methane, then ethane, propane and butane. You get the same name repeated through all four groups. So you have meth, then eth, then prop, then bute. And their chemical formulas, well, CH4, C2H6, C3H8. Now, using these chemical formulas, we can then define the general formula. So what we want to do there is we want to say if we've got n carbon atoms, then we ask ourselves how many hydrogen atoms should we get. So it's a little bit of algebra really. And on inspection, you can see, well, you've got 1 carbon, 4 hydrogen, 2 going to 6, 3 to 8. Well, there's a pattern there, and we find that we've got for every n carbon, we've got 2n hydrogen plus 2. So using that, we can then, for example, predict the formula for butane, which is 4 carbon chain. So that would be C4, and then H, 2 times 4 is 8 plus 2 is 10. Okay. Next on our list is the alkenes. Again, notice there's no methene in this group. It's impossible to have a 1 carbon member here because in the alkenes you need a carbon-carbon double bond. Okay, so ethene is the first member in the group, but you can see there's a very simple pattern here, which is simply C for each carbon atom, there is twice as many hydrogens. Right? Okay. And again, very quickly we can predict the formula for pentene, which would be C5, 5 carbons, and then H10. The next group we looked at was the alcohols, carrying on with the same naming system: methanol, ethanol, propanol, butanol. Now, to decide the general formula here, first of all, just look at the carbon chains here on their own in black, ignoring the functional group. Okay, just look at that first of all. You can see for each carbon atom you have, well, we've got 1 to 3, we've got 2 to 5, we've got 3 to 7 hydrogens. So we've got H, and this time 2N plus 1, and then onto that we add the functional group. Now that does not need to be written in red when you're defining the general formula. That's just to highlight the fact that we're identifying in the general formula the functional group, which is very important because that dictates the chemical properties. Okay, so there's our general formula for the alcohols, and again, using that general formula, we can now predict the formula for butanol. So that's going to be 4 carbons in the chain, C4, and then 2 times 4 plus 1, H9, and then OH. And then finally, the carboxylic acids. Again, the same pattern. You've got methanoic, ethanoic, propanoic, and then butanoic. Those are the first 4 members in the group. And to identify the general formula, again, look at the black carbon chains, first of all, the carbon-hydrogen chains, and we see that for each N carbon atom here, we'll look at ethanoic and propanoic acid first of all. We've got twice as many hydrogens plus 1. And then onto that we're going to add our carboxyl functional group in red. So we've got COOH. This is slightly different from the other naming systems in that the first member in the chain has n equals 0. Okay, so this will be n equals 0, and then n equals 1, and then n equals 2, and then n equals 3. So our first member, which is methanoic acid, has C0, so n is 0, so that's 0, and then H, 2 times 0 plus 1 is H, which gives us HCOOH. So butanoic acid has n equals 3, which is C3, and then H, 2 3s plus 1, 7, and then COOH. Okay, let's just quickly summarize what we've been through in this lesson, because it's been quite a long lesson, but this is important. I stress questions on homologous series and defining or explaining homologous series come up all the time in the chemistry exam, and so you need to be able to say that a homologous series is a group of compounds or molecules which have the similar chemical properties, and they have these similar chemical properties because they've got the same functional group, and also that they have similar physical properties, and these physical properties change gradually as you move down the group. So you need to be able to identify these chemical and physical properties for the alkanes, for the alkenes, for the alcohols and the carboxylic acids. And finally, you should state that all homologous series should be represented by a general formula, and you should be able to define that general formula for each of the alkanes, alkenes, alcohols and carboxylic acids. Okay, so the 4 key points of homologous series is that the chemical properties are similar because they have the same functional group. Their physical properties are similar and change gradually as you go down the group, and they all can be represented by a general formula.